Data link protocols, flow and error control. This is a module in the course EP 1100, Data Communication and Computer Networks at KTH in Sweden. Data link protocols. Here we assume that the physical layer has delivered frames to the data link. So frames mean that we know the start and the end of messages that have been communicated from a transmission unit to a receiver. The data frame structure is the format of the protocol data unit that has been communicated from the data link sender to the data link receiver. This is not the same as the frame that has been sent on the physical layer. An issue to be dealt with here is data transparency, as we will see. Another function that the data link have to provide is flow control to adapt the sender rate to the receiver rate. As we see, there are reasons for the receiver not being able to receive data at the same rate as the sender can send it. The next function is to deal with the errors that can occur during the transmission of the data from the sender to the receiver. First, we have to detect whether errors have occurred or whether a frame has been received correctly. And if it's incorrect, we have to deal with it with some protocol. The fourth issue is the multiplexing of sources to a shared link. This is often referred to as multiple access control, and this will be dealt in another module. So first we look at the data link framing, the functions and the format of that. And then we look at one of the issues that need to be dealt with when considering the framing. Then we look at flow control. We start from the simple stop and wait protocol and extend that to get a better performance for long links by a sliding window. And then we consider errors. We look at the function to check whether a frame has been correctly received or not. And if a frame is received in error, then we have to handle that by some means of correction. So first, the data link framing. We assume that the frame has been properly delineated at the physical layer. For a synchronous link, there is a certain bit pattern reserved for indicating beginning and end of message. This bit pattern is also sent when the link is idle to make sure that the sender and the receiver are synchronized with respect to their clocks. For an asynchronous link, there is no signal sent when there is no transmission to be done. Therefore, the frame has to contain on the physical layer a preamble that gives enough clocking information so that the receiver can start to detect that there is an incoming waveform, synchronize its clocks to that waveform, and then start sampling the data, sampling the waveform to recover the data. In this second format, the frame length is not indicated by an end of frame flag. Instead, there's a length field in the header information of the frame that indicates how long the frame is, so that the receiver simply can count the number of bytes that should be constituting the frame. The contents of the data link frame are the same in both cases. There's a header with the protocol control information, which also includes addresses if the frame should be multiplexed to any one of a set of receivers. And in the case of asynchronous, this is also where the length field is located. Then there is a data, which is the data from a higher protocol level that is carried by the data link frame. And then there is a trailer used for the error detection, as will be apparent shortly. A complication that can occur for synchronous transmission is that the flags that are indicating beginning and end of frame and also idle channel may occur by chance in the data or in the protocol information. If that would happen, the physical layer would find a flag indicating start of frame and would then scan through the frame and would see this bit pattern and believe that it's the end of the frame and would truncate the frame at that point. You would then lose synchronization with respect to the frame boundaries. It can take some time before it again synchronizes and is able to deliver messages. So if this occurs, there could be several frames lost. So this problem has to be prevented. This is done by something called character stuffing. Character stuffing uses another reserved character called an escape code. We shorten it as ESC. We use the escape code to indicate that the character following the escape code is not a flag, but is just data. Of course, also the escape code could occur spontaneously in the data, and therefore we have to put an escape code also before a bit pattern which looks the same as the escape code. So this is the function of the character stuffing. Let me show an example. We take data in, so we have flag which occurs somewhere in a data link frame. So after character stuffing, the flag has been preceded by an escape character. If the frame has an escape somewhere in the data, then that escape bit pattern has to be preceded by another escape. Same thing if we would have both escape and a flag occurring back to back in the data. Well, each of those characters will have to be escaped by another escape character in front of it. And the same goes if there are two or more escape characters occurring by chance in the data link frame. This indicates that the frame length, as it has been created on the sender data link, will now be longer because we have inserted escape characters in there. When it comes to the receiver, there's no ambiguity any longer for what is a flag, because all the correct flags will not be preceded by the escape character. We can also distinguish the bit pattern which looks the same as the escape character because it will have an escape character in front of it. So the receiver function is very simple. Once it finds an escape character, it deletes the escape character and leaves the character behind it. So this goes both for escape itself and for the flags. There is another variant of this stuffing called bit stuffing. It works in the same way, but instead of inserting characters, the escape characters, it inserts zeros after 5 consecutive ones. The flag is namely a character which consists of the bit pattern 0 followed by 6 ones and a 0, and therefore a flag will not be found in the data link frame. The procedure of the receiver is similar to the receiver of character stuffing. Once the receiver sees a string of 5 ones, it will always delete the 0 following the 5 ones, because that 0 has been stuffed by the sender and is not a 0 that belongs to the data. So by either of these two techniques, character stuffing or bit stuffing, it's possible to ensure that the data link frame is transparent with respect to the flags that delimit the physical layer frame.